All right. Good morning, class. Hope you're all doing well. Um, Sorry this lesson is a bit early. I'm imagining that many of you are probably asleep at 10:30. Um, I've been getting messages on Discord at like weird hours from students, so I think that their sleep schedule is inverting. Maybe. Hey, Jackson. But I woke up early this morning because of a staff meeting on Zoom. And hey, Sofa. Uh, so I always try to. The staff meeting was on Zoom, and I always try to do something obnoxious before the staff meeting starts. So I made sure to turn my camera on and my mic on, and I gargled mouthwash. So I don't know if you've ever had any Zoom meetings where someone is doing something loud with their microphone on, but I thought it was pretty funny. It was amusing. Um, so we are not going to have class Monday, Tuesday, Wednesday of next week because of the final exam, quote, final exam. All right. So you'll be working in pairs on that. Let's see. The homework is posted. You can submit the quiz as well, which is just the daily items from this week. So yeah, you can actually start the final exam already if you want to. I think it's posted. So let's get down to it. I'm going to be doing questions 2 and 6 from the May 2018 Time Zone 2 IB Physics exam, paper 3. So let's see, question 2. Whoa, gust of wind. Student carries out an experiment to determine the variation of the intensity of light with distance from a point source. The light source is at the center of a transparent spherical cover of radius c. The student measures the light a distance x from the surface of the cover to the sensor that measures the intensity I of the light. The light source emits radiation with constant power, and all of this radiation is transmitted through the cover. The relationship between I and x is given by blah, which can be written as blah. Show that k equals 2 times the square root of pi over p. All right, so this first question is literally just algebra. So if I have I equals p over 4 pi quantity c plus x squared, then I can rewrite that as c plus x squared equals p over 4 pi I. So that's just inverting that. And then I take the square root of both sides, cx. I multiply both sides by that. The inverse of that to get square root of 4 pi over p times c plus square root of 4 pi over p times x equals 1 over square root of I. So we can see that this is k. Right here, it's the thing that multiplies c. So, and that's the same expression if I just pull out the 4. All right. The student obtains a set of data. So notice that they've linearized the graph. Okay. So what they're doing, so for part B, they've linearized the graph. So what they have here is they measured x. So they're letting y squiggle equal 1 over square root of I. And they're letting x squiggle equals x. So when we do that, our equation becomes, so the equation was 1 over square root of I equals kx plus kc, and they're letting 1 over square root of I be y squiggle, and they're letting x be x squiggle. So that means that the slope is k. So k equals slope. And furthermore, it looks like kc equals the intercept. All right? So let's see. So part I says estimate what C is. Okay. So to do that, I can see that C is equal to B over slope. That's just comes from dividing these two equations. So what I want to do is I want to go ahead and extrapolate this line so that I can get the so if I were to extrapolate that line of best fit, it looks like extrapolating the line of best fit, it looks like the intercept is roughly 5. And then the slope, it looks like it goes up roughly, it goes from 5 to 35. So the rise is 30, and the run is 25. Important here, it's 25 centimeters. Okay, so that means my run is 0.25 meters. Okay, so I can take that and I can get C. As far as the units are concerned, this is 5. Well, let me just calculate it first. 5 times 0.25 over 30. This is 0.04. And then the units would be 1 over square root of power from, actually, the units of C is the distance as a distance, so wouldn't that be meters? Okay, so that is C. That's the radius of the cover. I don't know why you couldn't just measure that directly, but that's an easy measurement. You would just use calipers or something. Okay, so we estimated C, and then part 2 says we want to determine the power to the correct number of significant figures, including its units. So we know that, so what do we know? We know that K is equal to 2 times square root of pi over P. This comes from this formula right here. So I can take that and I can solve for P. And if I solve that for P, I get K squared over 4 equals pi over P, which says that P equals 4 pi over K squared. Now K, I said, was the slope, and the slope was 30 over 0.25. So I just need to work that out. 4 times pi over and that gives P equals 8.7 times 10 to the minus 4 watts. Okay? So let's see. Cool. So now the last part says, explain the disadvantage that a graph of I versus 1 over x squared has for the analysis in BI and BII. So, yeah, what if we graphed B versus I versus 1 over x squared? Basically, what I would say is that if we look at this equation, we can see that the graph won't be aligned. The graph is not linearized. Okay? By graphing what we did, we made sure that it was linearized. Whereas if we graph it a different way, then it's not necessarily going to be linearized. So that makes it, kind of, it's easy to analyze lines because lines have clean-cut slopes and intercepts that we can relate to physical constants. So I would say something to that effect. All right, the second question I'm going to do is question 6. Hey, Christian. Thanks for waking up. All right, question 6. A wheel of mass 0.25 kilograms consists of a cylinder mounted on a central shaft. The shaft has a radius of 1.2 centimeters, and the cylinder has a radius of 4 centimeters. The shaft rests on 2 rails, with the cylinder able to spin freely between the rails. The stationary wheel is released from rest and rolls down the slope, with the shaft rolling on the rails without slipping from A to B. The moment of inertia of the wheel is blah. Outline what is meant by rotational inertia. So I would say rotational inertia is how difficult it is to start or stop an object from spinning. Okay, the mathematical formula for inertia is sum over mr squared. So when they say outline, they sort of mean give an intuitive definition. Okay. Part 2 says, in moving from A to B, the center of mass of the wheel falls through a vertical distance of 0.36 meters. Show that the translational speed of the wheel is about 1 meter per second after its displacement. So I would use conservation of energy to show this. The initial energy equals the final energy. The final energy is rolling kinetic energy, which is 1/2 times the quantity. It's 1/2 mv squared times the quantity 1 plus I over mr squared. Okay. And then the initial energy is gravitational potential. So we can see that the m's cancel out. G is 10. Y is 0.36. That equals 1/2 times v squared times 1 plus I, which is given as 1.3 times 10 to the minus 4, over m r squared. What was the mass? 0.25. And r, if we look at it, it's rolling about this radius. Okay, so that's the r that I'm going to use. That's the radius that it's rolling about. So notice how there are two radii here. There's the outer radius and an inner radius. I want to use the radius that it's actually rolling about, and because of the way it's set up, I'm going to use the smaller one. Okay, notice that once it gets to the ground, the flat track, it's going to roll about the bigger r value. Okay, so that inner radius is 0.012 meters. So I can take this and I can solve for the velocity, which I will do using algebra. And I get 1.25 meters per second, roughly. All right. 3, determine the angular velocity of the wheel at point B. So we have omega equals v over r. That's the condition for rolling. So I have 1.25 over 0.012. And that's 104 radians per second. All right, now we're moving on. That was part A. Now we're moving on to part B. Oops, maybe you guys couldn't see that. Let me show my work. Christian asks, how's the knife furnace? Pretty good. Actually, the only thing I'm waiting on before I can start forging is the steel. So I actually ordered steel last night, and so whenever the steel comes is when I'll start trying to forge something. And also I've been sort of like keeping my eyes peeled whenever I'm like around train tracks or anything like that, because I'm looking for scrap metal that's just kind of lying around. So let me know if you have any scrap metal. All right. The wheel leaves the rails at point B and travels along a flat track to point C. For a short time, the wheel slips and a frictional force exists on the edge of the wheel as shown. Describe the effect of F on the linear speed of the wheel. Okay, so basically the issue is that notice how the radius starts to change. Okay. The radius starts to change. So we have V equals omega R. Okay. And initially, before it leaves this rail, it was rolling about a small radius, given its rotation. Okay. But then all of a sudden, it's going to be rotating about a bigger radius. Okay. So the R value changed. It went from let's see, where does it say? The radius went from 1.2 centimeters to 4 centimeters. So R went up. So what that means, if R goes up, when it leaves the rails, it's still spinning at the same rate. So omega is going to stay the same, but then the radius all of a sudden jumps up. So we can see that the linear speed of the wheel is going to want to go up. Okay? So actually that means that the frictional force is going to tend to increase the linear speed, because the radius went up but the omega stayed the same. What's going to be the effect on the angular speed of the wheel? So you can see if the wheel is spinning this way, okay, and there's a force, a frictional force that's propelling the wheel forward, okay, then that means you can see that this force is going against the direction of rotation. So that would tend to decrease omega. All right? Because it's doing a counter torque. Basically what's happening here, have you ever like taken a ball and spun it and let it hit the ground, and when it hits the ground, because it's spinning, it jumps forward? That's basically what's happening here. We have something that's spinning, and then it hits the ground and it's going to jump forward. All right, so that is my lesson for today. I'll send out a reminder later on once I'm done teaching my last lesson for this morning about the final. And I hope you guys have a great weekend. I hope everyone's doing well. Probably going to make some phone calls this afternoon because there's some people who I haven't heard from. So I won't be calling you guys because you guys are watching. But so have a really good weekend. Bye now.